Hello. Hello. So now today we are going to start the intensive NEET revision session 2, part 2. In part 1 I already discussed about the basic concept of the isomerism. Okay. So in isomerism you know that what kind of the topics are important, and if you are not aware about the topic and the importance of that topic, please revisit the video and you will get it. Okay. So now today we are going to discuss about the INR 2, that is the intensive NEET revision session of the 2, and today we are going to discuss about the organic chemistry. Okay. And when we talk about the organic chemistry, then now I am going to talk about here the something. I'm going to give you some kind of the basic introduction of the chapters what we are going to discuss today. So we are going to discuss about the hydrocarbons. Okay, not in the depth manner, but we can discuss what kind of the topics are important from this chapter for your last moment preparation. And after getting the idea of the hydrocarbons stand for, we are going to discuss about all the three sections like alkanes, okay, alkenes and alkynes. Fine. Okay. And after this, we are going to discuss about the next chapter from the class 12th, which is called alkyl halide and aryl halide. Okay. That means you can say that halogen contained compound. Okay. Halogen contained compound. In class 12, this chapter is also considered as a haloalkanes and haloarenes. Okay. Then after the third chapter, we are going to discuss about it, which is called alcohol, phenol, ether. Okay. So we are going to do this. We are going to discuss this chapter here also. And this chapter is actually considered in the class 12th as a chapter named alcohol, phenol, ether. And after getting the idea of all these things, then we are going to discuss about the next topic, which is called aldehyde, ketone. Okay. And the both part of this chapter like aromatic aldehyde and aromatic ketone. Fine. So, and then after the chapter is called acid and their derivatives, and then the one chapter is also known as amines. Fine. So this is all about the sections we are going to discuss today's only, but remember it, this is not in a depth way, but we are going to cover all the kind of the important topic from this chapter so that you can revise your last session and you will get confident about the organic chemistry. So now let's see, if we talk about the chapter called hydrocarbons. Okay, so if you talk about the hydrocarbons, so what are the more important topics and how we are going to cover it? Okay, see, in hydrocarbons, you know that the three portions are there. The one portion is called alkane. Okay, and in alkanes you have to prepare for the three topics. First one is their physical and chemical behavior. Physical and chemical behavior, which I already discussed in the last video, how to tackle the problem like boiling point, melting point, order of the organic compounds. So you kindly go and revise once. Then after, lab preparation, how we are going to prepare the alkane into the lab. Okay, and the third one, their chemical properties, that means which is known as chemical reactions. Fine. So this is the alkane portion. Similarly, the second part of this is alkenes. In alkenes, we are going to discuss same thing like their physical and chemical behavior. Okay. Then their lab preparation and then their chemical behavior. That means chemical reactions. Okay, and similarly the third portion is also there, which is known as alkynes, and same thing here also we are going to discuss like physical and chemical behavior, then lab preparation, and then after their chemical properties, chemical reactions. Make sure one thing, in the hydrocarbon, the most important section in all the three parts is alkanes. Okay, you have to take care of the alkane portion, is so much as an important section of the hydrocarbon. And if you know what, if you know the important section from the alkane, then there is no need to memorize think about the alkynes, because all the reactions are common in the alkanes and alkynes nearby, and alkane is a completely separate section. Okay, so this is the way through which we are going to discuss hydrocarbons. Now the thing is, how we are going to discuss about it. First of all, I already told you in the last class, keep in your mind when the number of carbons are same, when number of carbons are same, okay, this is a case 1. When the number of carbons are same, then keep in your mind, number of carbon in a straight chain is directly proportional to boiling point, directly proportional to solubility, directly proportional to surface area, and directly proportional to hydration enthalpy, and inversely proportional to rigidity, and inversely proportional to melting point. Okay, I already discussed in the last section. And you know what, the number of carbon in a straight chain, then it is going to be happen, and number of carbon in a straight chain inversely proportional to branch. That means what is going on during the straight chain phenomena, that is completely inversely proportional to the branch phenomena. The meaning is very simple. When the number of carbons are same, then how you are going to deal with some physical properties like boiling point, solubility, surface area, and everything. So kindly keep in your mind that when the number of carbon in a straight chain, then boiling point is getting higher, but in a branch, it is getting inversely proportional to the straight chain. That means in a straight chain, boiling point is getting higher, then whenever the branch is there, boiling point is getting lower and melting point is getting higher. Okay, so this is one of the best concept through which you are able to comment on the boiling point and melting point order of the different kind of the hydrocarbons. Am I clear? So keep in your mind all these things. Okay, so actually I already discussed in the last section also, so kindly revisit once, and again I am going to revise here also, so then you can go with it. Okay, so like see, suppose one question is here, one hydrocarbon is written in this manner, this is called P, and then another hydrocarbon is written in this manner. Okay, now you can see 1 2 3 4 5 6 carbon, 1 2 3 4 5 6 carbon, this is called Q, and then another carbon is here. Okay, and now you can count the number of carbon here also. How many carbons? 1 2 3 4 5 6. So all these three compounds contain 6 carbon. Now they are asking about, kindly explain their boiling point order. Okay, what is the boiling point order for these three molecules? So as we know that our basic relation is there, when the number of carbon in a straight chain, then the boiling point is higher. So that we can say that, can you tell me in all the three compounds which one has the largest straight chain? So sir, easily we can see here, it has two branch, it has one branch, there is no branch, that one is a complete straight chain. If it is a straight chain, then the boiling point of the P should be higher. Then after, if you are going to compare between the K, Q and R, then you can see in the R is branching is more, in a Q branching is less. Then in comparatively, if you are going to study about the Q and R boiling point, then you can say the boiling point is Q is higher than the R. Why? Because in R the branching is more. And similarly, if you go with the melting point of these question, what is the melting point of order? Then you know very well, whatever the property is getting changed during the straight chain of the position, it is inversely proportional to the branching of the carbon. So then we can say that the melting point is higher for where the branching is the maximum. Then the order should be R, then after Q, and then after P. So this is the way through which we are going to compare between the boiling point and melting point of the different kind of the hydrocarbons. Okay, and case 2, when number of carbons are different. Okay, So when number of carbons are different, then keep in your mind, as much as number of carbon is getting increases, boiling point is getting increases and solubility is getting decreases. The ultimately thing is simply, you can say that as much as molecular mass is getting higher, the boiling point is getting higher and solubility is getting lower. And this concept is going to be applicable only when the number of carbons are different. Okay, the Rips properties are remain same. Suppose you have a two kind of the organic compound in which what 2 carbon chain is there and the second option is 3 carbon chain is there, then the boiling point should be maximum for the 3 carbon chain in compared to the 2 carbon chain. Okay, so please keep in your mind, these are the so much important section for all of you. Done. So you can expect these kind of the question in the coming NEET examinations. They are going to ask you, suppose there are 4 and 5 compounds are there and one kind of the boiling point order they are going to ask you. So you have to take care of the simple concept. When the number of carbons are different, then you can go with it, and when the number of carbons are same, then you can go with it. Okay, so please keep in your mind, by this short way you are able to predict the boiling point and melting point of the different kind of the organic compound. Okay, one basic thing please keep in your mind, when you are going to solve these kind of the questions, please take care of the one thing also which is called the case 3. If you take about the case 3, what is the case 3? When groups are different. When groups are different. Suppose there are so many organic compounds are there and they are saying please find out the boiling point order. So all the concept like case 1, case 2 is there, okay, there is no issue. When the groups are different, when all the particular, suppose 4 compounds are given to you and in all the 4 compounds groups are different. So when the groups are different, then how you are going to deal with it? So keep in your mind, there only one concept is going to be possible to define all the character, which is called hydrogen bonding. Okay, so whenever the hydrogen bonding is getting higher and higher, the boiling point is getting higher and higher. Are you getting my point? So boiling point is going to depend on the hydrogen bonding, and I think all of you are aware about it. Hydrogen bonding is defined by 3 atoms, FON, phone, and whenever the phone is getting connected with the hydrogen, then a kind of the bond is going to be happen. That bond is called hydrogen bond. Okay, so keep in your mind, when the groups are different, please take care of the hydrogen bonding. When the hydrogen bonding is getting formed, then the boiling point is getting higher and higher. Because why? Because when the new bond is getting formed, one extra bond is getting formed, which is known as the hydrogen bonding, which is responsible for their more stability. That's why the boiling point is getting higher and higher. Okay, so please keep in your mind, and as well as they are going to ask you about the solubility order also. So as you know that whenever the hydrogen bonding is getting possible in a compound, then due to the hydrogen bonding, association is going to be happen, and due to the association, the solubility is getting higher and higher. Okay, so whenever the ultimate thing is simple, whenever the groups are different, okay, whenever the groups are different, please keep in your mind ki this compound is capable to form the hydrogen bond, yes or no. If the compound is capable to form the hydrogen bond, that means it is getting associated with the solvent molecules, and due to the more association, the solubility is getting also increases. Okay, in solution chapter you know that whenever you are going to immerse the solute into the solvent, the two kind of the concept is going to be happen, either dissociation or association. So due to the when association is going to be happen, when the hydrogen bond is going to be formed. So due to the hydrogen bonding, association is there, that's why the solubility is getting also increases. And due to the formation of the hydrogen bonding, one extra bond is getting formed, and due to the one extra bond formation, the boiling point is also getting higher. Okay, so please, whenever you are going to deal with the question like boiling point and melting point from the organic chemistry, you have to take care of the 3 things. Case 1, when the number of carbons are same. Case 2, when the number of carbons are different. And case 3, when the groups are different. So if you keep these 3 concepts in your mind, you are able to arrange the order of the solubility, boiling point, melting point, these kind of the questions from the organic chemistry. Okay, so please keep in your mind. So whenever you see the question, first of all, please check out, is there number of carbons are same or not. If the number of carbons are same, then you can go with it. And now if the number of carbons are different, then you can go with it. And when the groups are different, then you have to take care only one thing, hydrogen bond is getting formed or not. Is it? So this is all about the scenario through which you are going to find out the boiling point, melting point, and stability order of the hydrocarbons and other organic compound also. Okay, now the thing is, after getting the physical and chemical behavior of the organic compound or hydrocarbons, now the next thing is how we are going to form the alkane in a lab. Okay, so if you form two alkane, suppose you want to form alkanes in a lab, how you're going to form it? So alkanes can be formed by different kind of the method. I'm going to give you some kind of the basic examples. Like the supposed first example is there. Sir, I have alkenes. Okay, suppose you have alkene. This is alkene, and you want to form the alkane. Can you do one thing? I think all of you are aware about it. If it is an alkene, I'm going to do one thing. I'm going to take one reagent called nickel powder at 200 degrees Celsius. This reagent is also known as Sandrin-Sevatier reagent. Okay, and it is one of the best reducing agent ever. So it is going to add hydrogen. Okay, so this is going to add hydrogen. So then where you are going to add the hydrogen, so then double bond is there, where there we are going to add the hydrogen. Because why? Because single bonded compounds are saturated and double bonded and triple bonded compounds are unsaturated. So keep in your mind, whenever you see double bond and whenever you see triple bond, then these kind of the hydrocarbons are called unsaturated hydrocarbon. So they are actually unsaturated, so want to be saturate. Okay, saturated stand for single bonded compound. Okay, these are more stable. Saturated stand for we are completely satisfied. So all the unsaturated compound want to convert into the saturation, because of one of the most basic destiny for the organic compound to get the more stable product. So whenever you see the unsaturation in the organic compound, just convert the unsaturated compound into saturated compound, you will get your answer. Okay, so now you can see here, I want to form alkanes. As you know that alkanes stand for single bonded compound. Okay, so single bonded compound means saturated. So if I want to form the single bonded compound, just keep unsaturated compound with you, and in this unsaturated compound you just convert this unsaturated into saturated, you will get alkane every time. So that's why I am taking here unsaturated hydrocarbon, which is double bond, and I am going to pass with the nickel 200 degrees Celsius temperature, which is going to add the hydrogen on the double bond, and then we will get alkanes. Done? So this is the first. Like suppose I need to convert this compound also in a different manner, like CHCHR. Okay, suppose this is a compound, and again I want to convert into the alkanes. This is the next we are going to apply the next reagent. See, these are all the patented reagent. Okay, the catalyst we are going to utilize during this reaction all are patented. So on the basis of the patent name, the reagent's name is getting changed. Like in this case, you can see the nickel 200. I already told you that this is called Sandrin-Sevatier reagent. Okay, in many number of the cases, this reagent is also considered as S square. Which reagent? S square. So what is the full form of the S square? Sandrins and Sevatier. Okay. Similarly, in this second case, suppose this is also again alkene, and I want to convert this alkene into alkane. I am going to take another reagent. I am going to take palladium with hydrogen. Okay, so on the surface of the palladium, we are going to absorb the hydrogen. On the surface of the palladium, we are going to absorb the hydrogen, and that hydrogen is going to participate in a reaction as a reducing agent, and again this hydrogen is going to add into the double bond, and this unsaturated hydrocarbon is going to convert into the alkanes. Okay, so this is another kind of the process we have. Then there are so many options we have, like this is Rx, then this is 2Na with XR, and here we are going to utilize dry ether as a solvent. So whenever you see this is an alkyl halide, this time I am going to prepare the alkanes by the help of the alkyl halide, and I hope all of you are aware about it. When alkyl halide, two molecules are getting interconnected with each other via help of the sodium with dry ether, then this halide with sodium is going to be escaped. Then we have R and R, and it is going to form alkane. So what you will get the product? RR, which is also considered as a alkane. And I think all of you are aware about it. This reaction is called Wood's reaction. Which reaction? Wood's reaction. Okay, so always remember that in the Wood's reaction, if you are considering this R and this R, suppose I am taking here R dash, so then we can prepare the two kind of the cases in this case. How we are going to prepare it? Remember that when you are going to convert Rx to sodium with XR dash, and again you are going to pass this compound with dry ether. So now what is the difference between these two? Actually it is also the patented sodium with dry ether. It is a patented with the name of the Wood's reaction. Wood's name of the scientist is Woods. So we are going to form the R and R, which is called the alkane. Okay. Now you can see here, in this case, I'm going to do one thing. Here R equal to R dash. That means the both R1 I'm taking in this reaction, both carbon we are taking in these reactions are same. And when the both carbons are same, we will get simple symmetric alkane. Okay. But when you know, when you are going to pass alkyl halide 1 and another alkyl halide, and in this case, R is not equal to R dash. Okay. So here you can see R equal to R dash. Here R is not equal to R dash. And in this case, when we are going to mix these two particular alkane halide, alkyl halide, what you will get now? So you can see here, the both R and R dash are different. Then it is called unsymmetrical addition. Okay. Unsymmetric hai na yahan pe? Because the both carbons are different. So when the unsymmetric carbon is going to combine with each other by the help of the Woods reaction, you know, this you will get alkanes. But you know, here you can see the product. Here you will get different kind of the alkanes. Like when R and R is getting combined to each other, it is called RR. Or R dash is getting combined with each other to form the R dash. Okay. And another product should be also there, R dash. That means you can see here, you will get three different kind of the product. Okay. But here, by this case, you will get only RR dash. Got it? So now you can see, whenever the both carbons are symmetric, you will get one kind of the alkane which is called symmetric alkane. But when you are going to mix the two different kind of the alkyl halide in the unsymmetric manner, you will get different kind of the hydrocarbons. Okay. So this is a mixture of hydrocarbons. This is the mixture of hydrocarbons. And as you know that in the hydrocarbons, the all compound contain the same kind of the double bond, single bond. So then their boiling points are so much close to each other. So we are not able to segregate all these hydrocarbon in a different part. So that's why Woods is suggesting to you, please, whenever you are going to define the reaction, keep symmetric hydrocarbon during the reaction. So the main concept of the Woods is, please don't utilize asymmetric hydrocarbons. Okay. So that means Woods is far better for symmetric addition in compared to the asymmetric addition. So please don't apply this in the Woods reaction. If suppose you will get a question in the coming NEET examination, what happens when we are taking the asymmetric hydrocarbon during the Woods reaction? Then you are able to give the answer, because whenever we are taking the asymmetric hydrocarbon during the Woods reaction, whatever the product we are getting here, it is a mixture of the hydrocarbon, and we are not able to segregate this hydrocarbon. So in this case, we are not able to say that which product is going to be formed. So we are actually getting confused in this area. That's why for the Woods reaction, we are going to consider only symmetric hydrocarbons. So ultimately the final answer is, whenever you are going to form the alkanes via Woods reaction, this Woods reaction is only valid for the symmetric addition, not for the asymmetric addition. Are you getting a point? So this reaction is one of the most important reaction ever. Okay, Woods. Done? Okay. How the next method through which we are going to form the alkanes? See, if you want to form the alkanes, then we have another method called Rx with Zn plus XR dash. And here again we are taking the dry ether. Now you can see now, the same thing is going to happen here again, but the reagent is getting changed. Why? Because all of you are aware about it. Once the catalyst is getting utilized in a reaction which is called specific, all the catalysts are specific in nature. So everywhere we are not going to utilize all these things. And this is also the patented. So whenever you are taking the sodium with the dry ether, this is patented with the name of the Woods reaction. And here we are going to utilize the zinc in place of the sodium. So what will happen here? The same thing is going to happen like the Woods reaction. And what you will get? RR dash with ZnX2. Okay. So now you can see the product is look alike same, but the method is different. And this method is considered as Franklin reaction. Which reaction? Franklin reaction. So what is the difference between the Woods and the Franklin? See, via Franklin you are able to form the asymmetric hydrocarbon also. This is the one of the best thing. Correct? In the Woods reaction, if you are taking the asymmetric hydrocarbon, you will get the mixture of the hydrocarbon. But in this case, it is not possible. You can take the symmetric as well as the asymmetric. So that's why I can go with this. This method is far better than the Woods reaction. And you know what? In this Woods reaction, you will get one side byproduct here also, which is called 2NaX. Okay, now you will get 2NaX. So now you can see here you will get RR dash with the 2NaX, because 2Na X, sodium halide, and all of you are aware about sodium is more reactive. So in this case, whatever you are going to getting the product, that is the impure product because sodium is also available there. But here you can see zinc is the heavy metal, density is higher, you are able to remove it very easily. So I think the Franklin is a far better than Woods, okay? But in NCRT, Woods reaction is having more weightage than the Franklin. So keep in your mind, okay? Now, you can see again we form alkane, okay? So this is another method to form the alkanes, done? Now, suppose, okay, let's say, suppose you need to find out alkanes in a different another method. What is our next method is there? So if you go with it, suppose you are taking CH3COONA, which is called the sodium acetate, and you are just considering the 2 molecule of this, okay? You are taking the sodium acetate 2 molecule, and if you are going to electrolyze this, okay, if you want to electrolyze, okay, I am going to electrolyze this particular 2 molecules in the presence of water. What you will get? The thing is very simple. If you want to define in a last moment, actual mechanism is also there, but there is no need to mechanize right now because you are in a last moment. Just do one thing, break down the molecule in this manner only. So what you will get? CH3CH3, you will get CH3CH3, which is called ethane. You can say this is again alkane, okay? Then CO2, what you will get? 2CO2, okay? And whatever you are getting here, it is at which position? Anode position. Okay, because during the electrolysis you need 2 plates, anode and cathode. So in anode you will get alkane and carbon dioxide. In cathode you will get NaOH with hydrogen gas. Okay, so this is the cathode portion. So maybe possible during a particular NEET examination they are going to ask you when we are going to electrolyze the sodium acetate in the presence of water, then at cathode what kind of the byproduct we will get? So at cathode you will get always NaOH and hydrogen. Again I am repeating it, at cathode you will get NaOH and hydrogen. And you know what, this reaction is also patented with the name of the one scientist called Kolbe's. So this reaction is called Kolbe's electrolysis. Which reaction? Kolbe's electrolysis. That means by this reaction you are also able to form alkane in lab, okay? But you know what, by this method you are not able to form the single carbon alkane like methane, okay? So keep in your mind, whenever you are going to form the alkane by the Kolbe's electrolysis, just keep in your mind you are able to form only more than 1 carbon alkane, okay? And also in a Kolbe electrolysis, any kind of a reaction, either it is an alkene or alkyne, you will get Kolbe electrolysis reaction in all the chapter, alkene, alkyne, everywhere. So in Kolbe's electrolysis, please keep in your mind, cathode carried byproduct sodium hydroxide and hydrogen, and anode carried alkane and carbon dioxide. If you are forming the alkane, you will get alkane at anode. When you are forming the alkene, you will get alkene at anode. And when you are going to form alkyne, you will get alkyne at anode. Ultimately, anode you are getting your more major product. At cathode, it will always remain intact. In cathode, what you will get? NaOH and hydrogen gas. Again, I am repeating it. They are going to ask you during the electrolysis, Kolbe electrolysis, at cathode, which kind of the byproduct we are getting here. So always remember NaOH with hydrogen. Okay. So this is a Kolbe electrolysis. So these are so much important reaction by the name, like Woods reaction. Then after Franklin reaction, when we are going to define the Woods reaction, then please keep in your mind we are not taking the asymmetric hydrocarbon. When we are taking the asymmetric hydrocarbon in Woods, what you will get? Mixture of the hydrocarbon. That's why Woods is only valid for the symmetric addition. Okay, the second one is Franklin reaction, okay, where we are using the Zn, and the third one is the Kolbe electrolysis. These are the one of the most important section, okay. If you are talking about the hydrocarbon, these reactions are so much important for all of you. Done? Okay. Now suppose you want to form alkanes in a different manner. How we are going to form it? So now you have a different kind of the concept also to form the alkane. How, sir? So let's say, suppose you have aluminium carbide, okay, or you have barium carbide. These two carbides are there, and whenever you are going to mix this carbide with the water in excess amount, okay. Again, I am repeating it. Whenever you see aluminium carbide or barium carbide, and you are going to combine this carbide with the water in excess amount, always remember that you will get CH4. What you will get? CH4. What you will get? CH4. Okay, so that means always by this method we can form alkane. So this is another kind of the method which is most important for all of you, because they are going to ask you which carbide is capable to form the alkane in lab. So keep in your mind, two carbides are capable to form the alkanes in a lab. One is called the aluminum carbide and the second one is called the beryllium carbide. Okay, so this is another important section. So this is another way through which we are going to form the alkane in lab. Now how we are going to form the alkane in a lab in a different manner, in the other method also. So let's say you want to form the alkanes. Okay, so if you want to form the alkanes, then how you are going to form the alkanes in a different manner? After getting the idea from the Woods reaction, after getting the idea from the Kolbe electrolysis, now the next method is here, which is called Core-House synthesis. Okay, which one? Core-House synthesis. See, this is not as much as important according to the NEET syllabus, but you have to take care of the Core-House synthesis. In a Core-House synthesis, what will happen? Suppose you are taking alkyl halide, okay, and you want to form alkane from this alkyl halide, and what you are going to do? You are going to do one thing. You are taking R2CuLi, okay, R2CuLi. R stands for carbon, so I am taking R dash, and you know what? In Core-House synthesis, you are free to do one thing. What's the? Because you can take R equal to R dash, it is also valid. And if you are taking R is not equal to R dash, it is also valid. That means via Core-House synthesis, if you are able to form the symmetric alkane, you can form it. If you want to form the asymmetric alkane, you can also form it. That means there is no restriction in the Core-House synthesis. But in Woods, there is a restriction, you have to form symmetric alkane only. But here, you have to form any kind of the alkane. You are free to do whatever you want to do. So just pass this compound. Okay, when you are going to pass this compound, what will happen? The Cu and Li is there. You have to multiply here 2Rx. So now you have a 2 halogen. Okay, 2 halogen negative charge. Copper is metal and lithium is also metal. So copper can pass with the halide Cux, then Lix. Okay, so both metal can be removed out by the help of the halide. Then what you will have? 2R and R2 dash. So finally you will get 2R dash. Now you can say this is alkane. Got it? And if the both carbons are same, then you will get symmetric alkane. If the both carbons are different, then you will get asymmetric alkane. So this is one of the most important part, because in this scenario, you are free to form any kind of the alkane, either it is asymmetric or asymmetric. Symmetric or asymmetric. Done? So this is another. According to the NCERT, it is not as much as important, but please keep in your mind. Then the next one is, you have to form the alkane in another way also, which one is called by Grignard reagent. Okay, so by Grignard reagent you are also able to form. How, sir? See, this is Grignard reagent. I think all of you are aware about it. In this Grignard reagent, you know one thing, this is metal and non-metal, because magnesium is metal, halogen is non-metal. So here which kind of the bond is going to be formed? Ionic. And here carbon and magnesium is there. Carbon and magnesium, carbon is going to form which kind of the bond? Covalent. So which one is a weaker bond for all of you? Covalent bond is a weaker. So you have to break the Grignard every time from this particular bond. Okay, so whenever you are going to define the reaction of the Grignard, please break down the molecule from this particular bond only. So you will get Mg plus and R minus. Okay, so suppose anyone asks you why we are going to break the Grignard reagent from this bond only, because we are not able to form, we are not able to break this bond because the magnesium and halogen is there. One is metal, second is non-metal, ionic bond is going to be formed. So we need more temperature to break down this. But here the covalent bond is there, so that's why this bond is getting break very easily. So this is a Grignard concept. Okay, so whenever you are going to define the Grignard reaction in future in a coming chapter, you have to keep in your mind how we are going to break down the Grignard. Now the thing is how we are going to form the alkane from the Grignard. So let's say whenever you see Grignard reagent attached with any compound, again I am repeating it, whenever you see Grignard reagent is going to react with any compound in which sulfur, oxygen, nitrogen or halogen, in which sulfur, oxygen, nitrogen, halogen is getting interconnected with hydrogen. This hydrogen is called active hydrogen. Okay, or this hydrogen is also known as acidic hydrogen. So ultimately the thing is, whenever Grignard is going to react with, again I'm repeating it, whenever Grignard reagent is going to react with any compound which contain active hydrogen, how you are going to identify active hydrogen? So whenever the hydrogen connect with the sulfur, oxygen, nitrogen, halogen, because you know all these elements are electronegative. So the ultimately thing is, whenever the hydrogen came into contact of the electronegative atom, this hydrogen is called the active hydrogen or acidic hydrogen. So whenever the Grignard reagent is going to react with any kind of the compound, whenever the Grignard reagent is going to react with any kind of the compound which contain active hydrogen, just do one thing, this R minus and this active hydrogen, do you know, if these are the electronegative element, they are going to pull the electron. So this bond is going to be break, then you will get H plus. That's a simple concept. So that means Grignard, R minus, and you have active hydrogen. So this R minus and H is going to combine to form RH. And this RH is nothing, it is alkane. So whenever you want to form alkane via Grignard, you can do one thing only, just pass the Grignard reagent with those kind of a compound which contain active hydrogen. If that compound contain active hydrogen, you will get alkane by default. So this is one of the best method to form the alkane in a lab. Is it? So by Grignard you can also form the alkane. Now the next is there called decarboxylation. This is one of the most important according to the NCERT. Okay. So how we are going to form the decarboxylation? What is the decarboxylation? See, D stand for remove. What is carboxy? That is a carboxylic group. Okay. If you are able to form, if you are able to remove the carboxylic group from the given compound, you will get alkane as your final product. How, sir? Let's say, see, you have acid. Why you are taking the carboxylic acid? Because I need to remove the carboxylic acid only. So I have to take the carboxylic acid. And this carboxylic acid is going to react with the sodium hydroxide. What you will get? So you will get plus minus. This one is plus minus. Why it is a plus? Because this hydrogen is active hydrogen because it is connected with the oxygen. So what you will get now? So you will get RCOO minus Na plus. Okay. This is called sodium acetate. Now after getting the sodium acetate, what you will get? See, this sodium acetate is going to pass with the sodium hydroxide again in presence of calcium oxide with a high temperature. What you will get? See, this portion is getting removed out. Okay, this portion is getting removed out. What you will get? Na2CO3. So byproduct you will get Na2CO3 and remaining is R and H. So what you will get now? RH. This is called alkane. See, this is called decarboxylation. So ultimately, what is the decarboxylation reagent name? So decarboxylation reagent name is NaOH with CaO. This is a decarboxylating reagent. Okay. So in exam paper, if you see in any reaction, NaOH and CaO is combinedly exist in the reaction, you can say decarboxylation is going on. And during the decarboxylation, what you will get as a final product? Alkane. As a byproduct, sodium bicarbonate. Done. So this is another method through which we can form the alkane in the lab also. So ultimately, there are so many methods through which we are able to form the alkane. Done? Okay. So these are the formation of the alkane by the different kind of the methods. Done? Okay. After getting the idea of the formation of the alkane via different kind of the method, now the thing is how the alkane is going to react. See, so now we can talk about chemical reactions. Okay. So when we are talking about the alkane, what is the alkane? RH. And you know this RH contains sigma bond. Sigma bonded means saturated or unsaturated. So this is called saturated. That means it is highly stable. And if it is a highly stable, then these alkane is not able to react. Because by default if I am stable, then why I need to react with anyone? But if I want to react with anyone, I can do one thing only. I can react, but please keep my stability as it is. So that's why all the saturated compound is going to react by two ways. The first one is called substitution and second one is called elimination. Okay, and we are going to discuss substitution by the two way. One is called SN1 SN2. Okay, and elimination can be defined by two way. One is called E1 E2. Are you getting my point? So ultimately, whenever you see any alkane and you want to react that alkane, then you have to react that alkane by substitution or elimination. Okay. If the substitution is going on by the free radical, then one another kind of the substitution is there, which is called free radical substitution. Okay. So all kind of the alkane is going to define the reaction by these ways. Okay. Now, sir, where we are going to identify free radical substitution is going on. So whenever the free radical substitution is going on, please keep in your mind how you are going to identify. There is no need to mechanize all these things, because there is a mechanism, but we are not going to discuss here because it will take more time. So how you are going to identify? If you see the reaction, then how you can say, okay, sir, free radical substitution is going on. So free radical substitution, for the free radical substitution, you need to only identify two concept or two condition in the reaction. First, temperature is more than or equal to 200 during the reaction. If you see any reaction is going on at 200 or more than 200 degrees Celsius. And the second, if you identify sunlight or ultraviolet rays is available there. That means during a reaction, if you see the temperature is more than 200 or equal to 200, or whenever you see sunlight and ultraviolet, sunlight or ultraviolet is available during the reaction, then you can say without any hesitation, that means, sir, free radical substitution is going on. That means if you are able to identify these two conditions in any reaction, you can say that reaction is called free radical substitution. Is it? So this is one of the easiest way to define all these things. Okay. Now, if you define the free radical substitution, so free radical substitution, you will get like one example here. I'm going to give you one example. Like you have CH3CH3. Okay. And I'm going to pass this compound with the chlorine in the presence of H nu. What is the meaning of H nu? So now you can identify H nu equal to nothing. Is sunlight, energy. E equal to H nu according to the structure of atom. So this is H nu stand for, you have sunlight. Then you know that this is a sunlight is there. Then you are free to say, yes, this reaction is defined by the free radical substitution. So you have to substitute. What you are going to substitute, sir? Definitely hydrogen. Okay. So you are going to substitute the hydrogen. So then what you will get? You will get CH3CH2Cl. Got it? And if you are going to remove this hydrogen or substitute this hydrogen, you will get the same product according to the nomenclature. So this is called monochlorination. What is it? Is monochlorination. Okay. So you can see in the last 3 to 4 years, you can go through the NEET paper and you will get, there are so many questions from the monochlorination. They are going to ask you, if I am going to combine this hydrocarbon with any halogen, we will get monochlorinated product. Then how many monochlorinated product is possible? So this is the monochlorination, and the monochlorination or the monobromination or the monohalonation, monohalogenation. If you are going to substitute by any halogen, so you need monohalogenation or any kind of the substitution in the presence of sunlight is called free radical substitution. This is a mechanism name of this reaction. Okay. And how many kind of the monochlorination product is there? How you are going to judge it? Let's say, suppose you have a compound like this. Okay. And I am going to pass this compound with the chlorine in the presence of sunlight. Again, I can say, sir, sunlight is available. That means free radical substitution is going to happen. Now the thing is, the question, how you are going to define the monochlorination. So now you can see, first of all, you need to do one thing. Just keep the number on this carbon so that you can easily identify. Suppose, sir, I want to substitute this hydrogen. Okay. Okay. Let's see. Substitute it. What you will get? CH3, CH2, CH2, Cl. This is a one monochlorinated product. Correct? Okay, sir. Sir, may be possible. If I am going to substitute this hydrogen, then what will happen? Okay, try once. So I am going to substitute the second position hydrogen. So what you will get? You will get this one. Suppose I am going to substitute this kind of the hydrogen. Okay. So third one. Okay. Keep your number with you only so that you can easily identify. Substitute the third one. So you will get substituted here. You will get this CH3, CH2. Okay. And again, suppose you want to substitute this fourth one. You want to substitute this fourth one, what you will get? CH2Cl, CH2, CH2, CH3. I think these kind of the products are possible in totality. Now, if you go with the IUPAC nomenclature system, I think all of you are aware about the IUPAC nomenclature system. So now you can see where you are from where you are going to start the numbering. Sir, this is the group. So definitely this is the group. So definitely I am going to start from here, number 1. Now you can see here, this is the group, correct? Now you can see the chlorine in the which position? Second position. If you go with the position number, in this chlorine in which position? First position. In this chlorine in which position? Second position. In this, if you go with the numbering, then you can see if you start with this, because this is not a right numbering according to the IUPAC, you have to start from here only. So you will get chlorine at second position, and if you go with it, you can start from here only. Again you can see chlorine started from first position. So that means you have 2 position first, like one is this one and the another one is this one. So that means the both are same. You have to remove any one. So I am going to remove it because both are same actually. Here you can see the position in position of chlorine in second position, and here again you can see the position of chlorine in the second position. Again you have to remove any one, so you will get ultimately 2 products. So that means only 2 products are possible in this case. Not more than 2 products is possible in this case. So this is all about the scenario how you are going to define the monochlorination. So ultimately you have to take care of the things like, okay, when you are going to define the monochlorination, you have to think about it, okay, how we are going to substitute the chlorines to get the different kind of the product, not same kind of the product. If you are getting the same kind of the product which is getting neglected already, so please be aware when you are going to define the monochlorination or any kind of the monohalogenation. Okay, so ultimately this is your choice, from which hydrogen you are going to remove. These kind of the question you will get it in the NEET examinations. Okay. And also one thing is there, suppose you are getting the 2 product, okay, the one product is called P and the second product is called, now they are going to ask you, out of these 2 product, okay, out of these 2 product, which one is major in nature? Which one is major in nature? Major means more stable product. Major means more stable product. So now you can see these 2 compounds you have. Okay, so now you can say I'm going to form in a different slide. You have 2 product. Okay, by monochlorination you will get 2 product. This is, I already told you, this is a P, and second you are getting CH3 CH2 CHCl CH3. Okay, and I need to find which one is major. You can see now chlorine is an electronegative atom. It is going to withdraw the electrons. So which kind of the effect is going to happen? Minus I. It will be minus, it will be plus. Similarly, here chlorine is again going to withdraw the electron. Again, which kind of the effect? Minus I fit. Again, this is a positive charge. Okay. Now the thing, this is a positive charge, and next to this positive charge carbon, this is alpha. In alpha, how many hydrogen you have? 2 hydrogen. So here hyperconjugation number is 2. Okay. Here you can see this is a positive charge. Next to this positive charge is alpha. Next to this positive charge is alpha. Here you can see the 2 alpha carbon, and in this 2 alpha carbon, how many hydrogen you have? In this alpha 3, in this alpha 2. The total number of hyperconjugation number is here is 5. Okay, and you know very well, I think, more hyperconjugation number is more stability. So if you go with it, then which one is major product for all of you? So Q is a major product than P. So if you are going to define the monochlorination of this compound, you have to form Q in place of P, because Q is more major than P. Okay, so this is the whole scenario during the monochlorination or the monohalogenation. So they are going to ask you the question, how many monochlorinated product can form? So how you are going to judge it? Please remove the hydrogen or substitute the hydrogen by the halogen, and now you can check is there any common compound is available or not. If the common is there, please remove it. Then the next remaining different molecules are called different compound. Okay, and also keep in your mind which kind of the product you are going to be formed. So you are going to be form only the major product, and how you are going to form the which monohalogenated product is major? By the help of the hyperconjugation number. What is the hyperconjugation number? Whatever the carbon you are thinking about, next to that carbon is called the alpha carbon, and you have to find out the number of hydrogen on alpha carbon. You will get the hyperconjugation number. Done. So this is all about the alkane. So in alkane you will get these kind of reactions so in a continuous manner. Okay, so generally in alkane you have to define the substitution by a free radical. So first of all, I already told you that all the saturated hydrocarbon, Okay, all the single bonded compound can define free radical substitution. Now you know what is free radical substitution and how you are going to identify this is the free radical substitution by the two condition. I already told you that whenever you see temperature is more than 200 or equal to 200 or sunlight or ultraviolet rays is available there, you can say reaction is going to passes with the free radical. How you are going to define the free radical reaction? So by the monohalogenation, I am going to give you one example here. Okay, and I think all of you are aware about it. Free radical reaction or free radical mechanism can be defined by three steps: chain propagation, chain initiation, chain propagation, chain termination. Chain initiation is stand for the reaction is going to be initiated. Propagation means they are going to be combined with each other, and the termination means at the moment when the product is getting formed. So it's maybe possible they are going to also ask you during the free radical substitution how many steps are possible. So only three steps are possible: initiation, propagation, termination. Okay, so free radical mechanism, free radical substitution has been done. So this is one of the best reaction, and you will get question from this zone. I am damn sure about it. Okay, so please keep in your mind in a proper way. Now, any single bonded compound can also define substitution or elimination. Okay, so I am going to discuss about the substitution or elimination. Let's see. Okay, so substitution and elimination. So if you're talking about the substitution, free radical substitution I already discussed. Now I am going to discuss about SN reaction. Okay, SN stand for N stand for nucleophilic, yani via nucleophile, and S stand for substitution. That means this time substitution is going by nucleophile. Okay, last time in a previous example substitution is going by free radical. That's why it is called the free radical substitution. Here substitution is defined by any nucleophile. So ultimately in this reaction you have to substitute one nucleophile with another nucleophile. This is called nucleophilic substitution, and I think all of you are aware about the nucleophile. Okay, and if you don't know, just keep in your mind, if you want to identify which one is the best nucleophile ever, just keep in your mind the larger size atoms or ions, the more large in size, either it is an atom or ions. If the more large in size, then dispersion charge value is higher. Dispersion of charge, which charge? Negative charge is max, and these kind of the ions or atoms are one of the best nucleophile ever. So ultimately, if you want to identify which one is the better nucleophile, just go with the ones like atom should be in a greater in size. If the atom or ion is greater in size, it is going to disperse more and more negative charge. Why? Because the more size is atom, the more area is covered by the atoms or ions is maximum. And due to the more area covered by the atoms or ions is maximum, that means more negative charge is getting dispersed. And the more negative charge is getting dispersed means one of the best nucleophile ever. Okay. So keep in short. So you have to identify what is the nucleophile. Done? Okay. So we are going to substitute one nucleophile by the another nucleophile. This reaction is called nucleophilic substitution. Okay. And this nucleophilic substitution can be classified by two ways. One substitution is called SN1 and second one is called SN2. Okay. So what is the meaning of SN1 and SN2? Let's say if you talk about SN1, okay, you know one chapter is called Haloalkanes and Haloarenes. I am going to connect the topic with the Haloalkanes and Haloarenes. Okay. So Haloalkanes and Haloarenes is just connected with the reactions mechanism. Okay. So after getting the idea of the SN1, SN2, even E2, you are also able to solve all kind of the question from the Haloalkanes, Haloarenes only. So that's why I already told you a maximum number of time I am actually telling my students कि please there is no please keep in your mind there is no boundary between the chapters of the organic. All the organic is a combined section, you know. So that's why please don't bifurcate the chapter by chapter. I am teaching you here everything chapter by chapter, but ultimately all the concepts are interconnected with each other in the organic chemistry. Okay. So now we are talking about SN1, and by the help of the SN1 we know by the help of the SN1 we are able to predict the reaction via substitution. Okay. So SN1, what is the SN1? You know S stands for substitution, N stands for nucleophile, and here one is called unimolecular. One stands for unimolecular. Meaning is very simple. That means this is a kind of the nucleophilic substitution reaction where one molecule is actually going to decide each and everything. That's why it is called unimolecular. So if it is called unimolecular, that means only one molecule is going to decide everything. And if only one molecule is going to decide everything, that means whole reaction is going to depend on only one molecule. If the whole reaction is going to depend on only one molecule, then this is called which order of kinetics? First order kinetics. I think all of you are aware about the first order kinetics according to the chemical kinetics. So why it is called unimolecular? Because the whole and soul of the reaction is going to depend on only one molecule. That's why it is called the unimolecular. And if reaction is going to depend on only one molecule, then it is called first order kinetics. So the meaning is very simple: nucleophilic substitution by first order. Okay sir, how we are going to do this? First of all, you have to identify when we are going to do this. Okay, so if you want to define SN1, please keep these conditions in your mind. Okay, please keep these conditions in your mind, because on the basis of these conditions you will get more number of the question in the coming examinations. So what is the condition? That means when we are going to define SN1, to keep in your mind, the first thing is stability of compound is directly proportional to SN1. What is the meaning of this? It's a very simple meaning. Whenever you see, suppose you have a 4 option and they are going to ask you which compound is capable to define more faster SN1. So if any compound is going to define the more faster SN1 if the compound is more stable. Ultimately, to identify which compound is going to define more faster SN1, you have to identify which one is more stable. The more stable compound it is, more faster SN1 is there. Okay. Second condition, only polar protic solvent should be there. Which solvent? Polar protic solvent. That means SN1 reaction is going to be happen only when the polar protic solvent is there. What is the meaning of the polar protic? Polar stand for the compound is which is getting polarized into the plus and minus, and protic stand for which is going to release H plus ion. Okay, yani any kind of the solvent which is going to polarize itself, that means getting breakdown into the plus and minus and going to release H plus ion, is called polar protic. Like example, if you want some example here, then example is like alcohol, like acid. Okay, these are such example you know very well, I think so. Alcohol can release the H plus ion, acid can release the H plus ion, so that's why it is called polar protic solvent. Okay. Third condition is does not depend on nucleophile. That means what kind of the nucleophile you are taking during the SN1 reaction, either it is a weak or strong, it doesn't matter. Correct? It doesn't matter, because I already told you initially ki SN1 means that reaction which is going to depend on only one molecule. So you already dependent on one molecule, and you already dependent on one molecule. What is? There is stability. Correct? So you already dependent on stability of the one molecule, then there is no need to depend on the next molecule, because it is a unimolecular. So that's why this SN1 reaction does not depend on which kind of the nucleophile you are taking. Is it? Either it is a strong nucleophile or weak nucleophile, SN1 matter nahi karta iske liye. So that means for SN1, nucleophile does not matter. Okay? Because again I am repeating it. It is the first order kinetics. So it is going to depend on only one molecule, and once you are dependent on the stability of the compound, then there is no need to depend on the nucleophile of the compound. If you are going to depend on the nucleophile here, then you are going to depend on two molecules, then it is not becoming unimolecular. Are you getting my point? Okay. Okay. So please, whenever you are going to define the SN1 reaction, please keep in your mind these three conditions are most necessary condition, and they are going to ask you, like this kind of a question is very famous. I think all of you are aware about it. Okay, if you go through the PYQs of the NEET examination, your NEET paper, you can see these kind of a question you will get maximum in number. Like always they are going to give you the 4 option, and they are going to ask you which one is going to define more faster SN1. So ultimately we know that SN1 is not going to depend on the nucleophile. SN1 is going to depend on the stability of the compound only. So I have to find out the stability of the compound. Is it? Okay. So when we are going to define the SN1, by these condition is going to be valid, then I am going to define the SN1. Okay. What is SN1? Let's say, suppose I am going to give you one example. RC, R dash, R double dash, X. Now you can see, this is a kind of the saturated hydrocarbon. Why it is called the saturated hydrocarbon? Because it is single bonded molecule. Okay. Okay. Fine. Okay, now I am going to take one nucleophile. Sir, why you are taking nucleophile here? Because this reaction is called the nucleophilic substitution. And if it is a nucleophilic substitution, then one nucleophile is getting substituted by the another nucleophile. So I need one nucleophile. Okay, I need one nucleophile here. That's why I am going to do this. Sure. So where is another nucleophile? So we are taking the one nucleophile from the external sources, and one nucleophile already exists within a compound. Which one? Halogen. I think all of you are aware about it. Halogen contain negative charge. Okay. So that's why it is also a good nucleophile. So I need to replace this nucleophile by this nucleophile. That's why it is called nucleophilic substitution. Okay. Now let's say. And which kind of the solvent you are going to take? You are going to take polar protic solvent. Polar protic solvent. I already told you about it. Okay. Now, sir, what is actually happening during this reaction? So let's see. See, nucleophile is ready to attack because nucleophiles are good attacker. I already told you, na, it has more dispersion of charge. So that's why it is more electron density ions. If it is a more electron dense ion, then it is going to attack on the positive charge in very fast manner because it is a more dense negative charge. Okay. So it is a good attacker. So nucleophile is waiting to attack on the positive charge. So my duty to provide positive charge in this molecule so that it can attack on this. So the step number 1, I know RCR dash, CR dash, X is there. Okay. I think all of you are aware about. In this molecule you can see now X is the halogen which is electron withdrawing group because it is electronegative. So it is going to pull the electron. If it is going to pull the electron by which effect? Minus I effect. If it is going to pull the electron, then what will happen? So it is going to be happen RCR dash, R double dash, this is positive charge and X minus. Got it? Sir, why the positive charge is going to be formed? Because you know, this positive charge is so much stable. Why it is called intermediate? And this intermediate is so much stable. Why it is so much stable? Because you know, this carbon is getting covered by the R dash, R dash, and all threes are carbon, and this carbon is unstable carbon, and the next to this carbon is alpha carbon, alpha carbon, alpha carbon, and all these three carbon contain alpha hydrogen. More hyperconjugation number, more stable. So that's why this intermediate is highly stable in nature. If it is losing the X minus ion, it does not mind, because if this carbon cation is no. If halogen is getting loose, I am getting positive charge, but even though after I am more stable. Reason? Because I have covered by the more alpha carbon hydrogens. So it is ready to form positive ions. Now you can see one thing. Here all carbon is going to form the 4 bonds, then hybridization is sp3. Here one bond is getting less, then this hybridization is sp2. sp2 stands for one p orbital is getting vacant in this area. Because initially it is sp3, now it is sp2. That means one p orbital is completely vacant here. Okay. Now step number 2, it is ready with the positive charge. Now nucleophile is saying, okay, now I am a good attacker, so I am going to attack on you. Now let's see what will happen. RC, R dash, R double dash. This is vacant orbital of the p and positive charge. Nucleophile is eager to attack on the positive charge. Now you can see here, you have two options to attack on the positive charge. Either you can attack from the front side or you can attack from the back side. Because of why? Both lobe is vacant. So this positive charge is actually exists on the both lobe. So ultimately this nucleophile can attack from the front as well as the back also. So that means the 50% chance attack from the front side and the 50% chance attack from the back side. That means in this case you will get two kind of the product. One product is look like this, RC, R dash, R double dash, NU, or second is RC, R dash, R double dash, NU. Now you can see here NU is in front side, here NU is the back side. That means once you are going to attack on the front side, you will get compound P, and whenever you are going to attack from the back side, you get compound Q. So now you have a two product, one is called P, one is called Q. Got it? And now you know what? This carbon is a chiral carbon because all bonds, all the groups are different. This carbon is also a chiral carbon because all the groups are different. Got it? The problem is that this compound is a kind of the version where the nucleophile is in right side. So suppose this is a D form and suppose this is a L form. And now you know very well that the formation of the D form possibility is 50%, formation of the L form possibility is 50%. Ultimately, 50% plus D is getting formed, 50% minus L is getting formed. And you know what? Whenever any compound contains the two mixture of the 50% D, 50% L, this mixture is called racemic mixture. And I think all of you are aware about racemic mixture is not capable to show optical isomerism. That means one question is going to be arise during the SN1 reaction. Whatever the product we are getting, that product is optically active or optically inactive. What is your answer now? So your answer should be optically inactive. And what is the reason behind it? Because in SN1 mechanism we are getting a racemic mixture. And due to the external compensation, racemic mixture is not capable to form the optical activity. So ultimately, how many products you are getting obtained from SN1? You are going to get two products, okay? 50% the D version and 50% of the L version. This is all about the SN1, okay? And you know what? Out of these two steps, the first step is slow and second step is fast. Why the second step is fast? Because nucleophile is there, positive charge is there. Nucleophile is not going to wait to attack on the positive because nucleophiles are good attacker. So that's why this is going to be faster attack. That's why this process is getting faster and this one is getting slower. And if you go with the chemical kinetics, whatever the reaction is getting slower in the nature is called RDS, which is called rate determining step. Ultimately, whatever the order of this reaction and the molecularity of this reaction can be defined by the RDS. And now you can see in this step, only one molecule is there. That's why this reaction is going to depend on only one molecule. That's why this reaction is called the first order kinetics. Done? This is all about the SN1. Now we can talk about SN2. Now what is SN2? So for the SN2, if you talk about the conditions, so generally for the SN2, all conditions are inversely proportional of SN1 condition in general case. Okay. In general case, I already told you, but because this condition is actually applicable in the many number of the compound. So whatever the condition you got for the SN1, SN2 condition is inversely proportional to the SN1. Like for the SN1 we need which kind of the compound? Stable compound. Then for SN2 which kind of the compound? Unstable compound. More and more unstable compound, more and more favorable SN2. In SN1 I need polar protic solvent. In SN2 I need polar aprotic solvent. Okay. Like in SN2 we need polar aprotic solvent. Okay, polar aprotic solvent. What is the meaning of the polar aprotic? Polar stand for, you know very well, polar stand for plus minus dissociation. Aprotic stand for the molecule which is not going to release H plus ion. If you are going to release H plus ion, polar protic. If you are not going to release H plus ion, polar aprotic. Some examples of the polar aprotics are very famous, like DMSO, like DMF, like crown ether. There are so many. Okay. So DMSO stand for dimethyl sulfoxide, DMF stand for dimethyl formamide. Okay. I am going to give you one example here also. Like suppose you are talking about dimethyl formamide, DMF. It is look like this: CH3, CH3, T. N, CHO. Correct? So this is called dimethyl formamide if you go with it. Suppose you need to find out that this is a polar protic or polar aprotic. तो CH3 CHNA CHO अगर हम लेते हैं, एक मिनट को, CH3 NCHO. ठीक है, जैसे मानो ये एक एग्जांपल है. If I am taking this example here, you can see now. This is a pi bond. The pi bond is getting shifted into minus charge and it is a plus charge. So it is getting polarized. So that means this compound is polar. No doubt. This compound is polar. But this compound is not capable to release H. Why? Because there is no any hydrogen which is active in nature. So that's why it is not capable to release H plus ion. So it is a polar in nature but not aprotic. That means this is why it is called polar aprotic. It is polar but aprotic, not able to release H plus ion. Okay. So these are the conditions. Like in SN1 reaction does not depend on nucleophile. Either it is a strong or weak, doesn't matter. But SN2 is going to depend on the nucleophile also. That means you can see in SN1 compound is compound should be stable. In SN2, compound should be unstable. Here we need in SN1 polar protic solvent I need. In SN2 polar aprotic solvent is needed. And in SN1 we are not going to depend on the nucleophile, but in SN2 I am going to depend on the nucleophile. Why? Because SN2 stand for, here the 2 stand for, SN1 means unimolecular, 2 stand for bimolecular. That means we are going to depend on the 2 molecules. So that's why it is a which kind of order of kinetics? Second order kinetics. Got it? So in SN1 we are going to depend on only stability of the compound, but in SN2 we are going to depend on a compound unstability nature, as well as we are also depend on the nucleophile. Are you getting my point? So basically in SN1 we are not going to depend on nucleophile, SN2 we are going to depend on nucleophile because we need nucleophile in this case. How we are going to define it? Let's see. If you want to define SN2, how you are going to define this? So like suppose one compound is there. I am taking one example here. Okay, suppose I have one example here. And this is halogen, okay? This is single bonded compound, so it is going to define the substitution. I need one nucleophile. Why you need nucleophile? Because substitution means one nucleophile is getting substituted by the another nucleophile. Okay? And which kind of solvent you are going to take? Polar aprotic. I am taking here one example, DMF. Okay? And I am going to define the reaction. How it is possible? Let's see. Nucleophile is ready to attack. Nucleophile is ready to attack. Now the duty of this molecule is to provide carbocation. If the positive charge is going to be provided with this molecule, then nucleophile is going to attack very fast. Done? Okay. Now let's see what happened here. R dash C CH3 H X. As we know, X is an electron withdrawing group, so minus I effect is going to be happen, and it want to be breakdown. But this time carbon is not going to lose this X. Why? This carbon is not going to be lose this X. The reason is very simple. Okay, I am going to give you one so that you can understand in a proper way. Okay, now let's see. If the withdrawing group is there, you want to break down this bond, but carbon is not going to lose a halogen. Why? Because carbon knows if halogen is getting released, I am becoming positive charge, and if I am becoming positive charge, then I don't have more alpha hydrogen here. You can see in SN1 case, more, if it is getting breakdown, more carbon you have more with alpha hydrogen. That's why it is feeling more stable, more safe, so it is going to lose a halogen. But in this case it is not feeling safe because it knows if halogen is getting released out, my bond is getting less. Correct? Right now I have 4 bond, I have complete octet. If I am losing the halogen and I become less octet, but the problem is that I am able to form the less octet, but I don't have alpha carbon hydrogen here. So that's why I am feeling more unstable. So that's why I am not able to lose the halogen in this case. So now nucleophile is going to play one important role. Nucleophile, what is, I have to take which kind of the nucleophile here? Strong. Why, sir? Because halogen is not going to lose by the carbon, and nucleophile want to react with it. So definitely without losing the halogen, nucleophile is not going to be attacked. So if you are taking the strong nucleophile, the nucleophile is going to play the important role to remove this halogen. So keep in your mind, here nucleophile is needed as much as important. Why? Because without nucleophile you are not going to attack on this carbon. So ultimately nucleophile is going to take the first stance and going to attack from the carbon from the back side. Why not from the front side? Because already halogen is there. That means one nucleophile is already there. If you are going to attack from the front side, repulsion is going to be happen. That's why it is going to attack from the back side. And if it is a strong, then attack is so much strong so that halogen can pass. So what is going on here? So you can look like this. ये देखो, ये ऐसा दिखने लगेगा. Nucleophile is going to attack here from the back side. Halogen is going to remove from the front side. Got it? So nucleophile is going to attack from the back side. Halogen is going to remove. तो एक चीज और ध्यान रखो. Please keep in your mind. When you are very much strong, you are going to attack from the back side. Due to your high attacking force power, halogen is getting out. But you know what? This halogen is getting out easily. Then it is good for us. That's why whatever your halogen you are taking here, please keep in your mind, it should be a good leaving group. What is a leaving group? which can leave very easily. That means this is another kind of the favorable condition to define the SN2, because SN2 is strong, nucleophile is strong, there is no doubt. Nucleophile is going to attack very fast, but if you want this reaction is going to be smooth, then this particular halogen should be good leaving group, so that it can easily leave and nucleophile is going to be attacked very smoothly. Is it? So now what happened here? Let's see. You will get H, C, R dash, CH3 and U, and this halogen is getting replaced. You can see now. Got it? So that's why the more powerful nucleophile is required here, because if it is a more powerful, then their attack is going to be very much strong, and due to the strong attack, halogen or any other nucleophile is available here, it is going to be loose. Correct? But if you want to smooth reaction, keep in your mind whatever the nucleophile is there, please keep a good leaving group. Okay? Good leaving group means that has more size. If you want to identify what is a good leaving group, the greater in size. Because those nucleophile which is greater in size has a greater bond length, and due to the large bond length, it is easily break down, so the process is going to be smooth. Done? Now you can notice one thing. Here you can see methyl is in left side. Here also methyl is in left side, but here you see methyl is the right side. That means compound is getting inverted because attack is so much fast. It is look like this, like this is a molecule. If you are going to attack from the back side, what will happen? If you are attacking very fast, the molecule is getting inverted. So that's why it is going to be happen here. So molecule is getting inverted. So this product is called inverted product. So what is going to happen here? Inversion. And this inversion first time explained by the scientist called Walden. So this is called Walden inversion. Okay. So maybe they are going to ask you one question here. In SN2, which kind of the product we are getting? Inverted or non-inverted? So we are getting inverted product. Okay. But in SN1, there is no inversion is there. The compound is as it is. There is no inversion. That's why this kind of the product is called retention. This process is called retention. Okay. Remember it. So this is called retained product. Okay. Retained product. And this is called invert product. So in SN2, inversion is going to be happen. Why inversion is going to be happen? Because attack from the back side. And through the more stronger attack, compound is getting flipped or inverted. Okay. Are you getting my point? Okay. So that means there is no any kind of the possibility to form the racemic mixture here. So SN2 product can be optical active in nature. Okay. So this is all about the SN2. Now you can see it is a single step reaction. Only this reaction is going to happen in a single step. But that SN1 is a multiple step reaction. And you know what multiple step reaction is called? The complex reaction. Okay. So this is the kind of the reaction, and you know what? This is only a single step reaction. That's why this step is also called RDX. This is the slowest only because we have only one step. So if it is a RDX redetermining step, then you can see now this reaction is going to depend on two things. One is nucleophile, second is molecule. If reaction is going to depend on the two molecules, then it is become bimolecular. That's why SN2 is the second order kinetics. Done? So this is all about the SN1 and SN2. And how you are going to identify where we are going to define the SN1, where we are going to define the SN2. So you have all kinds of the conditions with you only. I already taught you each and everything. So to define SN1, compound should be stable. To define SN2, compound should be unstable. For SN1, polar protic solvent is needed. For SN2, polar aprotic solvent is needed. For SN1, nucleophile does not matter. For SN2, nucleophile should be matter and nucleophile should be strong. Okay. And for SN2, good leaving group is there, then it is well and good. Like suppose one you will get one example here. Like suppose one molecule is look like this and one molecule is look like this. Okay. And is there anyone going to ask you which out of these two compounds, which one is going to define more faster SN2? More faster SN2. As you know, single bond is there, substitution is going to be happen, and halogen is there. Halogen is a good nucleophile. Okay, so nucleophilic substitution is going to be happen. But the thing is, you know what? In iodine and chlorine, iodine has a larger bond length because iodine atomic size is more than chlorine. It has a larger bond length, so bond is getting weaker. So it can easily leave. So that's why iodine is a good leaving group here. Good leaving group here. Correct? And chlorine is not a good leaving group. Then suppose you want to define a reaction, then iodine is going to lose very fast. So this reaction is going to be very much smooth. So where SN2 is getting faster here? P. So why? Because iodine is a good leaving group in compared to the chlorine. Is it? So I hope you understand what is SN1, what is SN2, how we are going to define the SN1, how we are going to define the SN2. Okay. Now the next one is, we have one another reaction is called elimination. E1 elimination and E2 elimination. Okay. So I can assure you one thing. If you go with the NCERT, you will get a very simple comparison. Okay. मैं आपको एक comparison दे ही दे रहा हूँ. Let's see. देखो इधर. In a short way, you have to think once. Always remember, E1 is equivalent to SN1 in many number of the cases, and second, E2 is just follows the condition like SN2. That means if you are aware about the SN1, you know the condition of E1 also. If you know about the SN2, you know the condition of E2 also. And what is E1, E2? E1 stand for elimination and 1 stand for unimolecular. Again, this is a kind of the elimination which is going on, and it is a unimolecular. That one depend on only one molecule, so it is a first order kinetics. And what is the E2? Now you understand what is the 2 here? Bimolecular. It is a second order kinetics like SN2. Okay, that's why I am saying there are so many conditions are common in both E1 and SN1, E2 and SN2. Okay, so I'm not going to define the condition here, but keep in your mind. See, for SN1 and for SN2, okay, for SN1 and SN2, I need nucleophile. That's why nucleophilic substitution is there. But for E1 and E2, I need base. Okay, so please keep in your mind, in the presence of nucleophile, nucleophilic substitution is going on. In presence of the base, elimination is going on. So this is the one of the basic difference between the substitution and elimination. Elimination is always happen when the base is available there. Okay, so that's why the reason base are those. See, nucleophile, I already told you that nucleophile has good dispersion of charge due to the large size of the atom, so it is a good attacker. It is a good attacker. If nucleophile sees any carbocation, it is going to attack very fast. But you know what? Base is not a good attacker. It is a kind of the ions which is going to extract H plus ion. Correct? But it is not a good attacker. We are not a attacker. It is not going to be attack on anyone. So that means it's very simple to understand. If nucleophile is good attacker, then definitely it is going to attack very fast. So in this manner we can say all the SN1 and SN2 reactions are faster. And whenever you are going to define the reaction of the substitution by the nucleophile, this reaction should be faster in nature. While elimination is going to be slower, because it is not going to take any positive charge. It is going to wait to extract H plus ion. It is going to wait to extract H plus ion. That's why these kind of reaction is going to be very much slower. Okay, so eliminations are slow step, jabki substitution is faster step. And you know what? When the elimination is slower, then definitely it need more temperature. That's why all kind of the elimination is going on when the temperature is max. So when the temperature is getting max, then elimination is getting favorable. And you know what? Substitution is getting very much faster. So here we need minimum temperature. So now these are the simple difference between the elimination and substitution. So what is the difference between them? So in substitution we need nucleophile. In elimination we need base. Substitution is faster because nucleophile is good attacker. Elimination is slower because base is not a good attacker. It is going to extract the H plus ion from the compound. And that's why in substitution there is a faster, that substitution is a faster reaction, then there is no need of the high temperature to define the reaction. But while elimination is a slower reaction, then we need to apply the temperature to define the more fastest product. So always remember that if you see any kind of the temperature where the temperature is maximum is given to you, you can easily say that sir, this reaction is called elimination reaction. Or if you see any kind of the base is there, you can say it is elimination reaction. If you see the nucleophile is there, you can say the nucleophilic substitution reaction. Otherwise, the conditions are same for all. Like for SN1, we need more stable compound. Similarly, for E1, I need more stable compound. For SN2, I need more unstable compound. Similarly, for E2, I need more unstable compound. Okay, only the difference is between nucleophile and base. Okay, if you want to see any example, so I'm going to give you one example like even elimination. Okay, let's see. So suppose one molecule is there, CCH3 H CH3 CBr CH3 CH3. Okay, suppose I have one molecule here. Okay, now you can see now I am taking one base here. Okay, now let's see what will happen. As you know that, sir, in all the molecule it has electron withdrawing tendency, so definitely it is going to apply the minus I effect. It is getting bricked. If it is getting bricked, then what will happen? So step number 1, here you are taking base. So that means if you are taking base, then you are waiting for H plus ion. If you get H plus ion, you can accept it and leave it. So base is needed here because base is going to wait for the to extract the H plus ion. Okay. Okay, base is needed H plus ion. Now you can see base is waiting for the H plus ion. Now let's see how this compound is going to remove the H plus ion here. So start with this mechanism. CH3, CH3, C positive, CH3, CH3. Okay. Now you can see what is going on here. See, this due to the minus I effect, it is going to be removed out. So this became carbocation, and this carbocation is feeling more stable because of why? Because this carbocation is next to the alpha, next to the alpha, next to the alpha, and all alpha carbon contain more hydrogen. That's why this carbocation is feeling more stable. So this intermediate is going to be formed here. Okay. Done. This intermediate is going to be formed here. Now it is ready and Br minus is outside. Done. Now in step number 2, you can see now I am keeping this stuff very much in a slow manner. Okay. Now step number 2, this carbocation is ready. This carbocation is ready. Now base is there. Now base is saying, I am waiting for H plus ion. Please give me the H plus ion. So I think all of you are aware about the hyperconjugation. This carbocation is need to stabilize itself because carbon has less bonding here. So it is going to take help from the alpha carbon. So it is asking for him, from him, from him, and from him also. Now it is your duty if from which alpha hydrogen you are going to participate in the bonding. Okay. So let's see. Suppose you are going to take alpha hydrogen from this one. Suppose this is P, or you are taking hydrogen from this. Both is actually same. Either you can take from this or you can take from this. Both will going to form the same product. Or the second option we have, either we are going to take the alpha hydrogen from this one, which is called Q. Let's see how many product we are going to be expect. Okay. One is the P version, second is the Q version. P1 means we are taking the hydrogen from this alpha carbon, and Q means we are taking the alpha hydrogen from this carbon. So first I am going to form the P. If you are taking the hydrogen from this alpha carbon, what will happen? The hydrogen is going to remove out and bond is getting, like see I am going to give you. It is look like this only. So you are going to shift this hydrogen bond here, and then hydrogen is getting leaved out. So what will happen? This bond is getting shifted here. So what you will get? CCH3, CH3, C double bond, CH2, CH3. Okay. So what will happen? This base is going to accept this hydrogen. Okay. So you will get this product. And if you are removing the hydrogen from this alpha carbon, you will get Q. Let's see. So what will happen here? This bond is going to be shifted here. Hydrogen is getting released by accepted by the base. So what you will get? CH3, CCH3. This bond is getting shifted here. What will happen? You will get CH3, CH3. Correct? You can see now. And this, in this case, B case, base is going to accept this H plus ion. If you are removing the hydrogen from the alpha carbon of this, you will get P product. And if you are removing the alpha hydrogen from the Q, you will get this product. Now it is your duty to find out, okay, sir, that means in elimination we have a two option, we will get two product. Which product is good for us? So I already told you that in organic chemistry, I need to form more and more stable product. So you have to find out which one is more stable. So now you can see here the sigma bond, pi bond is there. You have to identify only resonance, correct? So you can see this is a pi, this is sigma, this is sigma. That means pi sigma 1 conjugation, pi sigma 2 conjugation. So here 2 resonating structure is going to be formed. But here you can see this is pi, this is sigma, this is sigma, this is sigma, this is sigma. So that means pi sigma 1 conjugation, pi sigma 2 conjugation, pi sigma 3 conjugation, pi sigma 4 conjugation. That means here 4 resonating structure is going to be formed. The ultimate thing is that here the resonating structure is max and here the resonating structure is minimum. As you all of you know that more and more resonating, more and more conjugation, more and more stability. That means Q is major than P. That means Q is called major product. So that means we are going to form which kind of the product in this elimination? By the Q1, correct? And you know what? In this compound you can see all where sigma bond is there. But after the elimination, you will get which kind of the bond here? Pi. That means the ultimately, what is the meaning of elimination now? The meaning of elimination is very simple. Conversion of the sigma bond into pi bond. But keep in your mind, when you are going to define the elimination, you need base. Okay. So what is base is doing? What kind of the scenario condition? Why we are using the base here? Because base is needed to remove alpha carbon hydrogen, because base is a kind of the ion which can extract the H plus and it is not going to attack. You can see you have a positive charge, but base is waiting here. Base is not going to attack on the positive charge. Base is waiting for the H plus ion, and by the hyperconjugation number, this carbocation is going to take the help from the alpha hydrogen. So it is now your duty which alpha hydrogen you want to remove it. The basic thing, I have a two option. Either I am going to remove this hydrogen from the P or from the Q. If I am removing the hydrogen from the P, I will get this product. If I am removing the hydrogen from the Q, I will get this product. And in this hyperconjugation, resonance is going to be maximum. That's why this is the major product. And you know what? In elimination, the major product is called Setje product. Which product? Setje product. So they are going to ask you in a many number of the examination, which one is called Setje product. So always remember that during even elimination, whatever the major product you are going to be form, the major product is called Setje product. Okay. The major product is called to be the major product from the even elimination is called Setje product. I hope you got it. Done. So this is even elimination. And how many steps are needed for the even elimination? 2 steps, E1 and E2. Okay, and every time you are getting stuck between which hydrogen we are going to remove it. So please keep in your mind, please remove that hydrogen by the base where you will get more resonating structure. And if you are getting more and more resonating structure, your product is getting more and more stable. That's why it is called the major product. So in even elimination, my first target is to form the major product, and that major product is called Setje product. Which product? Setje product. Okay. Now, if you talk about the E2 elimination, how we are going to do this? Let's see, I have one example for all of you. Okay, suppose I am taking this particular molecule and I am taking here base. Correct? This time, what will happen here? Let's see. Base is waiting, please provide me H so I can escape. The problem is that how it is going to provide it. Now you can see in the all compound this molecule is EWG, so it is going to apply the minus I effect. So definitely this bond is going to be break now. So let's see step number 1. HC H H Br H H. The problem is that minus I effect is going to be applied. But this time carbon is not going to lose the bromine. Why, sir? Because carbon knows if bromine is getting loose, I am become positive. And you know what? If I am become positive, I don't have alpha carbon. I have alpha carbon 1, but in this alpha carbon only 1 hydrogen is there. But here in even you can see, if I am going to remove this bromine, then it will become positive. Now you can see you have 3 alpha carbon. So you have more alpha hydrogen. So this carbocation is feeling more stable here. That's why it is ready to release the H plus bromine ion. But here it is not able to lose the bromine ion because it is this carbon knows if bromine is getting released out, then I don't have more alpha carbon, so I'm not getting stabilized. It is the exact same case in SN2 also. Why SN2 in SN2? Why halogen is not getting released out? Because carbocation is getting unstable. Similarly, this time why carbon is not going to release the bromine? Because it knows if I'm losing the bromine, my carbocation is getting unstable. That's why bromine is not going to be outside. So how the base is going to react here? So now base is going to take initiative. If you are not going to lose, then I am going to take the initiative. So that's why here base should be strong. Now you can connect the SN2 also. Similarly, in SN2, halogen is not going to be released, so nucleophile is getting more stronger, and then it is going to attack from the backside. So similarly here, if the compound is not ready to do anything, then base is going to take initiative. So in SN2, nucleophile should be stronger. In E2, base should be stronger. So if you are taking the more stronger base, then this base is not going to be weak. It is going to really remove alpha hydrogen first. So if alpha hydrogen, why alpha hydrogen? Because I know if bromine is going to be outside, this carbon became carbocation, then this carbon is called alpha carbon. So that's why the base is going to take that hydrogen. If hydrogen is getting loose, then what will happen? This bond is getting shifted in here. If this bond is getting shifted here, then what will happen? Let's see. CH3 double bond. You can see now. This bond is getting shifted with this carbon became double bond. Okay. Correct. And base is going to take H plus ion. It is getting released by a BH. If this bond is getting shifted here, what will happen? The next to the carbon is getting formed bromine, CH, CH. You can see now. If this bond is getting shifted here, so then this carbon has already 4 bonds. If this bond is getting shifted, then its carbon had 5 bonds, which is impossible. Now you have to release bromine because bromine want to be loose out. Now in this case, bromine should be loose. Yeah, bromine has to be loose because bromine knows that carbon became 5 bond, which is unstable in nature. So ultimately, I am going to inspire the bromine to remove out. So what will happen here? So you will get CH3 double bond CH CH. You can see now, and bromine is getting outside. Br minus. Okay, so this BH you already removed, which is getting combined with Br minus. You will get HBr and you will get B minus as a return. That means B minus is working as a catalyst in this case. Got it? So now you can see initially compound has sigma bond, now compound has pi bond. This is called elimination. And you know what? Why the base is going to take initiative? Because bromine is not going to be loose because carbocation is very much unstable. That's why base is so much stronger. It is going to take the participant, initiate the reaction. So it is going to release that hydrogen which is alpha carbon, because we know that whenever the bromine is getting released out, this carbon needed alpha carbon hydrogen. So that's why this base is going to remove the alpha carbon hydrogen. So it is getting shifted. So automatically bromine is getting outside. Okay. So this is E2 elimination. And you know what? SN2 is also in one step and E2 is also in single step. So there are so many similarities between SN2 and E2 via condition, but the one difference is there. We are taking base here. In nucleophilic substitution, we are taking nucleophile. Done. So this is all about the scenario. So ultimately you can think here, when we are going to take the E2 elimination when the compound is unstable, when we are going to take the E1 elimination when the compound is stable. Okay. In SN1 there is no need of the strong or weak nucleophile. In SN2 we need the strong nucleophile. In E1 there is no need of the weak or strong base. In E2 we need a strong base. So ultimately more similarities between the elimination and substitutions are there. Done. So I hope you got all the kind of the options here. Done. Okay. Okay. Now this is all about the SN1, SN2, and you know your whole chapter of the haloalkanes and haloarenes are actually combined with all these things. Done. Okay. Now, so in hydrocarbons we already formed alkanes, and how the alkanes are going to react with each other. I know that all the single bonded compounds saturated, how they are going to react by the 3-way nucleophilic substitution or substitution, elimination, or free radical substitution. So I already told you all the kind of the conditions. Now we can talk about alkenes. Okay? Alkenes. Alkenes are considered as RCH double bond CS2. Okay? That means it is saturated or unsaturated? Saturated. So how we are going to do the alkenes or alkynes reactions? So now take these particular points in your notebook. How we are going to deal with the alkenes? It's very simple. See, if you want to give the reaction of alkenes, how you are going to do this? If you want to define the reactions of alkene, keep in your mind. Case 1, if symmetric alkene is there, okay, and case 2, if asymmetric alkene is there. Okay, so whenever you are going to define the reaction, again I am repeating it, whenever you are going to define the reaction, so please keep in your mind if this alkene is symmetric or asymmetric. Okay, so when the alkene is symmetric, what we are going to do this? Like see, this is symmetric or asymmetric alkene? Symmetric, sir, because we are able to break the molecule into two equal parts. You have to do only one thing. Suppose you want to react with this alkene with any XY compound. Again I am repeating it. If you want to react this alkene with any XY compound, if compound is symmetric, just do one thing, up and down. That's it. So actually what we are doing here, because we know that we are talking about alkene, and alkene contain double bond. Double bond is called unsaturated, and unsaturated means unstable. That means it is going to define only one reaction called addition reaction. That means all the double bonded compound define addition, like all single bonded compound substitution elimination. Similarly, all double bonded compound define addition. So here what is going on? Addition only going on. And now you can see this is unsaturated, it became saturated. So your compound is became stable. So ultimately whenever you see the symmetric compound, just do one thing, up, down. Nothing. No need to worry anything. Just go with it. And whenever you see the asymmetric alkene like CH3, CH double bond CH2. Okay. And you want to define this reaction. Why it is asymmetric? Because we are not able to break the molecule into two equal parts. And easily identify, if you want to identify easily it is symmetric or asymmetric, just take the double bond. You can see both side hydrogens are different. This is asymmetric. Just take the double bond. Both side hydrogens are same, symmetric. Okay. If it is asymmetric, if the asymmetric hydrocarbon is there, and you are going to react this molecule with any XY. If you are going to react this molecule by any XY, like symmetric, you have to do only one thing, up and down. It is up to you. आप किसको ऊपर ले जा रहे हो, किसको नीचे ले जा रहे हो. It is your choice. Which one is going to attack up and which one is going to attack down. In asymmetric, whenever you see the asymmetric hydrocarbon and you are going to react this molecule with any XY, you have to follow these two reactions. One is called Markovnikov reaction, and second one is called anti-Markovnikov reaction. Okay. So when you are going to define Markovnik, when you are going to define the anti-Markovnik, you know what? Anti-Markovnik is also called crash effect. Okay. So identify. See, whenever you are going to define the anti-Markovnik, just follow one thing. Anti-Markovnik is going to be happen only in only one case where peroxide should be available there, and second, sunlight should be available there. So whenever you see any asymmetric hydrocarbon is going to passes with any kind of the XY compound and peroxide is available there and sunlight is available there, you can say without any hesitation that means anti-Markovnikov rule is going to be happen. Okay. And how we are going to identify Markovnikov? So basically whenever the peroxide and sunlight is not available, then you can say we are going to follow Markovnik. That means whenever you see the asymmetric hydrocarbon, then asymmetric hydrocarbon reaction is going to happen by the two way, Markovnik, anti-Markovnik. How to identify anti-Markovnik? Peroxide or sunlight should be there. How to identify Markovnik? When peroxide or sunlight is not there. Okay. So just follow this step. You are able to form all kind of reaction. Like see, suppose I am taking one example. CH2 double bond CH2 react with hypochlorous acid. And suppose anyone asks you, what is the product of this reaction? You can see this is the symmetric or asymmetric? Symmetric. If it is a symmetric, then you can do one thing, up, down. So what you will get now? CH2OH, CH2Cl. This is your answer. Done. No need to worry about anything. This is your final product. Done. But when you see asymmetric hydrocarbon like CH3, CH double bond CH2, and you want to react this molecule with a Cl. Now can you tell me, is there any peroxide? No sir. Is there any sunlight? No sir. If it is a asymmetric, then it is going to follow which law? Markovnik law. If peroxide and sunlight is there, anti-Markovnikov law. So what is the Markovnikov law? the Marconic law is there. It is getting breakdown plus and minus. The negative part of the reagent attack on those carbon where hydrogen number is less. So where the hydrogen number is less? Here 2, here 1. So hydrogen number is less here. So definitely negative part is going to attack on those carbon where hydrogen number is less. So what you will get now? CH3, CHCl, CH3. Got it? But similarly, if the same molecule is there and you are going to define a reaction called reaction with HBr in presence of peroxide and sunlight. Now you can say this is symmetric or asymmetric? Asymmetric. But right now you have peroxide and sunlight. That means you need to follow anti-Marconic. So if you need to follow anti-Marconic, then what will happen? So Marconic is stand for where the negative part of the reagent attack on those carbon where hydrogen number is less. So what is anti? It is opposite to the Marconic. Where the negative part of the reagent attack on those carbon where hydrogen number is max. So here you can see 1 hydrogen, here 2 hydrogen. So where hydrogen number is max? Here. So bromine is going to attack in this area. So what you will get now? CH3, CH2, CH2, Br. That's it. Done. So now you can see the difference here. What is the Marconic of rule? So Marconic of rule is where the negative part is going to be attack on the which hydrogen where the hydrogen number is less, or anti-Marconic is stand for the negative part of the reagent attack on those carbon where hydrogen number is max. The only difference is that you have to follow whenever you see the peroxide and sunlight, you can say anti-Marconic, and whenever you see without any peroxide and sunlight, you can say Marconic. So whenever unsaturated hydrocarbon is there, you just follow 2-step Marconic or anti-Marconic, and whenever the symmetric hydrocarbon is there, just do one thing: up, down, up, down. That's it. So this is the simple thing. Suppose I am going to ask you, can you tell me the answer of this reaction? CH2 double bond, CH2 plus HCl. Can you tell me the answer? So can you tell me this is symmetric or asymmetric? Symmetric. Up, down. So what you will get now? CH3, CH2, Cl. Done. This is symmetric. Up, down. Khatam. Okay. If suppose I am going to ask you CH3, C double bond, C, H, H, CH3. If the what is the answer of this reaction when we are going to pass this reaction with HOBr? Hypobromous acid. Okay, this is symmetric or asymmetric? Symmetric. So then you have to break up, down. It is up to you. Up kisko le raho, down kisko le raho. So what you will get now? CH3, CHOH, CHBr, CH3. So these are the simple concepts through which you are going to form the reactions. Done. So again I am repeating it. Whenever you are talking about the alkene or alkyne, that means double bonded and triple bonded compound, just do one thing. Find out the compound is symmetric or asymmetric. If compound is symmetric, just equally distribute up and down. If compound is asymmetric, just find out peroxide is there or not. If peroxide is there, then it is going to follow by the anti-Marconic. If the peroxide is not available, then it is going to follow by Marconic. Is it? Now next one. Now the next one. This is all about the hydrocarbons. In a short way, I am going to revise all the things. Okay. So after getting the idea of the hydrocarbon, how we are going to deal with it, in hydrocarbon one reaction is so much important, it's called ozonolysis. Ozonolysis. And what is this? Nothing to worry about ozonolysis. Via ozonolysis, I am going to identify double or a triple bond. That means if you want to identify the compound contain double or triple bond, yes or no, just find out via ozonolysis. Then you can say that if you want to identify that compound contain double and triple bond, yes or no, then go to the ozonolysis. How you are going to do the ozonolysis? Like see, I am going to give one example. Like suppose I have one molecule CH3 double bond CH3. Okay, and I want to do ozonolysis. Just follow one thing, very simple. In many number of the cases you can see now, they are going to give ozonolysis mein ozone with zinc with water. Okay. And they are going to utilize, in some cases, NaBH4, in some cases, H2O2. मैं सारा बता रहा हूं, ध्यान से समझो. Okay, how you are going to do the ozonolysis here? Okay, so ozonolysis stand for to identify double and triple bond. कैसे करोगे? Just break the double bond and distribute oxygen. Just break the triple bond, distribute oxygen both sides. That's the simple concept of the ozonolysis. So like see, it is a double bond, break the bond, just distribute the oxygen. So what you will get now? So you will get CH3, C double bond O, CH3. In the right side, what you will get? CH3, C double bond O, CH3. Now you can cross check what is going on. You are going to break the bond, oxygen oxygen distribution. So what you will get? CH3CO CH3, CH3CO CH. Sorry, यहाँ H है. Okay, so you are getting one aldehyde and one ketone. This is a simple concept. So what is the meaning of this? You are writing here. See, whenever you see NaBH4 is with ozone during a reaction, then you can say it is reductive ozonolysis. Which kind of the ozonolysis? Reductive ozonolysis. Matlab, after getting the ozonolysis product, you have to reduce the molecule. And when you are seeing H2O2, you can say it is called oxidative ozonolysis. What is the meaning of this? The meaning is very simple. After ozonolysis, whatever product you are getting, just oxidize the molecule. Am I clear? So ultimately, ozonolysis can be defined by the two way. One is oxidative and second is reductive. You have to identify this is oxidative and reductive by the help of the reagent. It is given with the ozone. Okay. And how you are going to define the ozonolysis? Just do one thing. Check out double and triple bond. Break that bond. Distribute oxygen. You will get the answer. Like suppose I am going to give you one example here. Suppose you have a molecule CH3, CH2, CH double bond CH2. Okay. Can you tell me what you will get after ozonolysis? Batao, what you will get now? Sir, double bond, oxygen, oxygen. What you will get now? CH3, CH2, CHO, and you will get HCHO. You can see this part is the different and this part is the different. Done. And if I am going to add here something like NaBH4, so now you know that this is a reductive ozonolysis. You have to reduce it. Reduce means you have to add hydrogen. So just keep electronegative atom on right side, left side. You have to add hydrogen. So what you will get now? CH3, CH2, CH2OH. All of you are aware about it. Whenever aldehyde is getting reduced, you will get alcohol. Whenever aldehyde is getting reduced, you will get alcohol. Got it? So that's why I am going to reduce it. Now I get final product. Again, if you are going to reduce this one, you will get CH3OH. So the thing is very simple. Whenever you see NaBH4, that you have to keep in your mind, after ozonolysis, whatever the product I am getting, if I have to reduce it. And when the H2O2 is there, then keep in your mind, whatever the product I am getting after the ozonolysis, I have to oxidize it. So that means ozonolysis can be defined by two way, oxidative and reductive. Done. And how you are going to do ozonolysis? Just find out double and triple bond, break down, distribute oxygen, you will get the product. So this is all about the ozonolysis. And this is all about the chapter called hydrocarbons, alkene, alkyne. In all the chapter, single bonded reaction is a segregated. I already explained by the SN1, SN2, E1, E2. Double, triple, you will see. Just keep two things in your mind. If the compound is symmetric, distribute equally. If compound is asymmetric, follow Marconic, anti-Marconic. Is it? So thank you to all of you. And this is all about the basic concept of the organic from my side, and these kind of the concept is going to help you a lot during the